Good morning everybody. We are back with fluorescence spectroscopy again. So, in this lecture we will continue with fluorescence quenching. In my last lecture actually we talked about we started with fluorescence quenching and we gave a basic idea of what is happening in quenching. So, if we just recall, then quenching is any process which decreases the fluorescence intensity of a sample. Sample means of course, it is a fluorophore, because we deal with fluorophore in fluorescence studies. That is the first and foremost. So, means when we do fluorimetry, then we say, the spectra looks like this. Say we have a fluorescence spectra of this sort. Say this is fluorescence intensity, and say this is wavelength. Okay, and suppose this fluorescence intensity plot is like this as a function of different wavelength. And if you go on adding, quencher, then maybe it will be quenched progressively this way. Okay. So, this is your fluorescence intensity when Q is 0, and this way Q increasing. Okay. So, fluorescence is decreasing. So, any process that decreases the fluorescence intensity is called fluorescence quenching, and the general term is luminescence quenching. Phosphorescence quenching may also in principle take place. So, that is why it is better to start with the term luminescence quenching. Okay. Now, the different processes which can result in quenching of luminescence or quenching of fluorescence is these are energy transfer. Energy transfer means that you have got a molecule in the excited state, and say in the excited state it transfers energy to another, say another molecule M primed. There are various mechanisms. There are various mechanisms by which this energy transfer can take place. Right now, I am not going into the details of it, but this will be one of the modes of fluorescence quenching. So, this is your energy transfer. So, what happens that as a result of this, your M star plus M primed, that gives rise to M plus M primed star, and then what will happen, this M star may fluoresce, giving rise to M primed in the ground state with H nu primed, or maybe it may so happen that it will go to the ground state by various non-radiative means. Okay. So, this is one of the one of the modes of fluorescence quenching. So, this is one, type 1. Okay. Type 2 is collisional quenching. Collisional quenching. Collisional quenching, which is also termed as dynamic quenching. So, what is happening that in the excited state, so molecule M star, and in the lifetime of this excited molecule, within tau of this, tau m, okay, or tau m star, whatever you say. So, another species which collides with this excited ensemble of M. Okay. and thereby it is getting deactivated. So, giving rise to so your quencher is there. So, then it gives you M in the ground state plus Q plus heat. Okay. So, you do not get emission for this. So, what is happening that maybe suppose say 10% of this M star is quenched due by this mechanism. So, you can expect it approximately a 10% reduction in fluorescence intensity of M star. Okay. So, progressively this will reduce, and you can expect the similar trend, I mean this increase, I mean decrease in the intensity. So, increase of quenching. This is one, this is another mode, and the parallel to this there is another mode which is called your complex formation, which is called the static mode. Okay. So, I will come to this in detail in due time. So, this is the second, and this is called this static quenching mode, and this is the third one. Fourth one will be which may be electron transfer. Fourth one is electron transfer quenching, although it is not written here in the slide, but note that there is another, I mean there can be another mode which is called electron transfer quenching. Okay, what is happening in that case? So, you have got M to M star I A after absorbing the incident photons, and then you have got a quencher which is a electron transfer quencher. So, it transfers electron to this M star, and in the excited state what is happening, that maybe its electron accepting capability is more, that is it is acting as a better oxidant. So, it accepts electron, and thereby in the excited state it gets reduced, and the reduced species, if it so happens that it is non-fluorescent after electron transfer, so that you will be having like something like a contact complex, and then it does not fluoresce, does not fluoresce. The example is pyrene. When you excite with say 340 nanometer light, it generates pyrene star in the S1 state. Originally it was S0. Then if you add dimethyl aniline DMA, okay, so dimethyl aniline NMe, so what will happen? It transfers electron, so that in the excited state a donor acceptor complex is formed. So, which is called exciplex. I will come to those things, I mean exciplex or excited state electron transfer, this with a separate heading, I mean in some separate lectures. Okay. But just giving you the idea that what is happening in electron transfer quenching. Okay. So, that means it is basically pyrene DMA, this is delta plus, this is delta minus, a complex is formed, and thereby original pyrene luminescence is reduced a lot. Okay. So, spectra may look like this is, say this is a pyrene emission. So, when you add more and more DMA, it will be like, so gradually it is reduced, and this band is okay. So, this band is decreasing and this band is increasing. with an isoemissive point. Isoemissive point, okay, like ISO's best, which is observed in case of your in case of your UV spectra. So, observation of an isoemissive point corresponds to an equilibrium in the excited state. Okay. So, this is your exciplex band, and this is your normal pyrene locally excited emission band. So, this is your lambda and this is your emission intensity. Okay. So, this way means if you look into this pyrene emission, you will be seeing that it is progressively quenched. So, this is as a result of electron transfer quenching. So, this is electron is transferred from the donor to the excited ensemble. So, reverse thing may happen, that the excited species may transfer electron give electron to a donor in the ground state. Okay. So, the reverse thing may also happen. So, this is just a story behind this electron transfer. I mean what is happening in electron transfer quenching. Okay. So, I just discussed various modes of quenching. Okay. So, quenching okay. So, what is happening that you have quencher over here and M star giving rise to M, and of course, quencher back. So, a number of processes can lead to the reduction of fluorescence intensity, that is one will be quenching. These processes can occur during the excited state lifetime, as I told you, for example, collisional quenching, energy transfer, charge transfer reaction, or maybe another thing which is important, that in the excited state if some reaction is taking place, so that your active species or the excited species population is reduced. Okay. So, in that case you can also expect to have a reduction in intensity. So, the one which I just have talked about is this pyrene DMA case is the charge transfer interaction. Energy transfer interaction I will come with a separate lecture. Just today I will just give you this idea of collisional quenching and also this ground state complexation, quenching due to ground state complexation. So, basically simple quenching, no complication due to energy transfer or charge transfer, or maybe reaction. Okay. So, these other issues I will take up later, but right now we will be dealing with this collisional and energy transfer, this complex formation quenching. So, we shall focus our attention in two quenching processes usually encountered. One is called your dynamic quenching, another is your static quenching or a complex formation in the ground state. This is called your ground state quenching mechanism. Collisional quenching occurs when the excited fluorophore experiences contact with an atom or a molecule that can facilitate non-radiative transition to the ground state. Common quenchers are O2, oxygen, iodide, cesium plus, acrylamide, then dimethyl. There are many examples. Okay. And iodide is the among different halides, it is the strongest quencher, because it is the heavier atom. So, heavier ion. So, that is why this is a very efficient quencher. So, M star, then quencher, then it's a contact between the M star and your quencher, and thereby it facilitates the non-radiative transition to the ground state. Okay. So, so basically you are having the excited state population, and you have given a pinch of this iodide I minus. So, what will happen, that iodide, generally what is happening, that suppose if there is no excited species, then in presence of iodide your molecule in the ground state will experience collisional interaction with this iodide, because probability wise I mean they will tend to collide with each other because of the motion within solution. So, what is happening because of their diffusional motion. Now, in this molecule plus iodide, if you shine with radiation, then your molecule will absorb radiation and go to the excited state. So, it does not matter whether the molecule is in the excited state or in the ground state, iodide will suffer quenching with, I mean will experience quenching, I mean collisional collision with the excited or with the ground state molecule. So, whenever there is collision there is possibility of energy transfer. Now, the idea is that if the molecule is in the excited state, then there is a possibility of non-radiative de-excitation through this collision. Now, the point is, if the molecule decays very fast compared to this possibility, I mean compared to the time required for the molecule, I mean for iodide to come close to it and have a collision. If this collision is frequency is slower than the frequency of deactivation, then deactivation or maybe frequency of deactivation through fluorescence emission, then this fluorescence will not be hampered a lot. But if its lifetime is such that within its lifetime it suffers collision with iodide, then non-radiative de-excitation will be there. Now, especially what iodine does is, iodine is a heavy atom. So, it will invoke this I mean it will allow this singlet triplet mixing, okay, which is called the spin orbit interaction, and spin orbit interaction will help this intersystem crossing as well. In addition to the IC process, ISC process will also be enhanced, and as a result of which excited state will be depopulated. Okay. So, quenching, we are talking about dynamic and static modes, and now this quenching process will require molecular contact between fluorophore and quencher. So, I mean there is a contact for dynamic or maybe if it is a static mode even. So, they require some kind of contact. Okay. There are other trivial types of non-molecular quenching, such as reabsorption of fluorescence in highly absorbing samples, or maybe if it is a very strong solution, I mean very concentrated solution. Now, since we deal with dilute solution in all our studies, we'll use dilute solution. Okay. So, that is why we are not going to consider all these complications. Okay. So, still we are in dynamic and static mode. So, dynamic quenching, collisional encounters between fluorophore and quencher, your M and Q. The quencher must diffuse to the fluorophore during the lifetime of the excited state. That is very important. Okay. So, within the lifetime of the excited state fluorophore, say this is your quencher and this is your fluorophore. So, it must diffuse to it, then have a collision. So, that means it is like this. Okay. So, this should happen. So, upon contact the fluorophore returns to the ground state without emission of a photon. So, when there is a contact, it goes back to the ground state without emission, although if it is not there, then it would have emitted some photon, but since it is a this collision, it will just go down to the go to the ground state. The distance over which the quencher diffuses is delta x, which is equal to square root of twice d tau, where d is the diffusion coefficient of the quencher, tau is the lifetime of the excited state of the fluorophore. That means those molecules or those quenchers which are on an average in this distance will suffer collision. Okay. I mean if this is a lifetime tau, then whatever distance it represents, so that much of distance within the lifetime a quencher will diffuse. So, that means the last collision will be suffered by by the excited fluorophore if the quencher is at least at a distance of this much. Okay. So, if it is more, then the possibility will be less, I mean the possibility will not be there. Okay. So, that is why diffusion coefficient, I mean that is related to the solvent property as also the property of the molecule itself. I mean if it is a very complicated structure, it is a huge structure, then diffusion will be affected. Okay. And static quenching, it is due to the formation of complex. Okay. And mechanisms of static quenching, mechanisms of static quenching is as I told you, formation of a complex between the fluorophore and quencher. Now, what is meant by complex? And complex is non-fluorescent and dark, that is also important. Now, what is meant by complex formation? Now, what is a complex? Say maybe you heard about, I mean compound is, say you can have many example, I mean like sodium chloride, HCl, etc., etc. And complex, maybe you can think of this cuprammonium complex. Why it is called complex? Because it is not a compound, and you know why this is a complex. So, a molecular complex is formed. Complex means it is different from a real compound. Okay. So, what is happening and what is happening that here in the ground state there is some kind of interaction. Some kind of interaction means it is maybe it may be non-covalent kind of interaction. There is no real covalent bond formation. Okay. So, what is happening that in this case this ground state molecule, ground state M, okay, ground state M will form. So, M before excitation. So, you have M, you are adding quencher. So, in the ground state everything is in electronic ground state, electronic. Still we have to reach M star. So, M star has not yet been achieved. I mean we have not put any photons from outside onto this solution. So, this is generally designated in this way with a dotted line which says that there is some kind of interaction. And what is the effect of interaction? That now if you shine the whole thing, because in this mixture you have M and you have MQ and you have also Q. Okay. So, if you give H nu, then this will be excited and MQ will also be excited. Now, the idea is that MQ is not fluorescent. So, no H nu primed, but here it gives H nu, I mean it gives rise to some photon. So, what is, I mean the thing is that if there in absence of any quencher your situation was like only M star, then H nu primed. So, suppose if in this case, suppose you are not changing the intensity of the incident light, okay, you are not changing. So, what you are changing is in one case you have M and in the other case you have MQ, M and Q. So, in this case if you shine with say 100 photons, then possibility, I mean if the efficiency of excitation is 100%, say you have 100 M star. So, you expect to have say 100 photons. In this case, in the other case M plus Q. Suppose if it is say 25% complexation. So, that means 75% M and 25% MQ. So, what is happening? You are shining, that means you have M star 75 and MQ may be star 25, and say if it is dark, means if it does not fluoresce, then what will happen, that you can expect that this 75 M star will give rise to 75 H nu prime. So, that means although in this case, unlike this collisional mode, okay, in the excited state, before the molecule goes to the excited state, it forms a complex or some interaction between this M and Q occurs, which results in formation of a complex, and that complex is dark, it is not fluorescing. So, if it is not fluorescing, then you also can expect a reduction in fluorescence intensity. Okay, so, this is another mode, unlike this collisional mode, this is another mode, that in this case you have a ground state interaction. If there is no ground state interaction, then possibility is the collisional mode. Okay. So, this complex is, so it is called, in many books you will be finding non-fluorescent, the term non-fluorescent, or dark complex, it is called a dark complex. Okay. So, if we recall, I mean normal Stern-Volmer expression, you see that if this any type of quenching is described by Stern-Volmer equation, and this Stern-Volmer, original Stern-Volmer formulation is based on the fact that it happens in the, this quenching occurs by means of collisional mode, and it is a bimolecular collision. I mean it is a collision between two molecules, one is M star, another is Q, and the quenching constant is the bimolecular quenching constant. Okay. F0 and F are the intensities in absence and in the presence of quencher, and of course this quencher is a dynamic quencher, rather than the static quencher or ground state complex forming quencher. Kq is the bimolecular quenching constant, tau 0 is the lifetime of the fluorophore in absence of quencher, tau is the lifetime of the fluorophore in presence of quencher. So, F0 by F equal to tau 0 by tau. So, I mean you can relate F0 with, actually it came from phi 0 by phi. Phi means here this quantum efficiency. So, phi 0 by phi equal to F0 by F equal to tau 0 by tau equal to 1 plus kq tau 0 into q, where tau 0 is the this lifetime in absence of any quencher. Okay. Q is the quencher concentration in moles, Ksb is the Stern-Volmer quenching constant. I mean it is called the Stern-Volmer constant, or in some cases you will be finding Stern-Volmer quenching constant. Okay. So, basically this Stern-Volmer quenching was developed with the idea that, I mean this quenching occurs in a collisional mode. Okay. So, this bimolecular quenching constant, the bimolecular quenching constant Kq is related to the diffusion controlled bimolecular rate constant. So, diffusion controlled rate constant as follows, where Kq equal to gamma into K naught, where gamma is the quenching efficiency. The bimolecular quenching constant Kq can be used to judge the efficiency of quenching. So, how efficient is the quenching? Okay. The rate constant K0, that is the diffusion controlled bimolecular rate constant. K0 is basically the diffusive flux of a molecule, provides a measure of the collisional frequency and is given by K0 is equal to 4 pi Avogadro number divided by 1000. So, this is the expression for K0, into Rf plus Rq into df plus dq. This df plus dq is the combined diffusion constant, and Rf and this the molecular radius of the fluorophore F. Okay. And a molecular radius means if we consider this to be a spherical system, it is easy to understand. Okay. And these are the diffusion coefficient of the fluorophore and Quencher, and n is the Avogadro number, that is 6.023 into 10 to the power 23. So, you see that if df and dq these are more, then k0 is also high, and radius, if radius is also high, then your k0 is also high. So, this way these are related. Okay. So, ultimately what we got is a Stern-Volmer expression, that is F0 by F is equal to 1 plus KSVQ. F0 is the unquenched fluorescence intensity, F is the fluorescence intensity in presence of quencher, Q is the quencher concentration, KSV is the Stern-Volmer quenching constant, and KSV is related to Kq by means of Kq into tau 0, where tau 0 is the fluorescence lifetime in absence of quencher, that is the radiative fluorescence lifetime. Okay. Okay. In the simplest case of collisional quenching, the following relation is called, is the Stern-Volmer equation, and is that holds good, where F0 and these are already known, Stern-Volmer quenching constant, and this should yield, if we plot F0 by F versus Q, this should yield a linear plot with a slope of KSV. Okay. So, this is a plot, it is a representative plot F0 by F versus concentration in mole. So, generally it remains linear, but under certain circumstances it may deviate from linearity. So, that deviation from linearity and the cause of that will take up in other cases, other day, but why that linearity is deviated? So, these are further complication, and from those deviation, those information, whether it is deviated upside or deviated downward, like if we have a plot of F0 by F as a function of quencher concentration, you may have like this if this is 1, you may have like this plot up to certain concentration, and beyond maybe in other case you can, after a certain concentration, you can expect a upward bend, or maybe you can expect a downward bend as well. Okay. So, basically these are the further complications, or maybe in some cases you may be finding that fluorescence initially increases and then it goes to maxima and then followed by a reversal in fluorescence. So, that is also observed very recently. So, these are the complications. So, those things I will take up separately, but right now we would just like to understand what is happening with simplest case. So, purely collisional quenching, known as dynamic, F0 by F is equal to tau 0 by tau. This is a standard relation. So, you should remember this very carefully. Should be very careful in discussing. Why I am telling you should be very careful, because I will be showing it to you that if there is a difference in mode of quenching, whether if it is dynamic or if it is static, then some characteristic change in lifetime as a function of quencher may give you the idea of whether this dynamic mode is operative or the other mode is operative. So, this lifetime information is very important in diagnosing whether the mechanism is purely collisional or purely non-collisional, or maybe it is a mixture, and a mixture can also happen. Okay. So, basically tau 0 by tau is equal to 1 plus k q tau 0 into q. So, basically this should be k q tau 0 into q, this should not be tau, this should be k q tau 0, where k q has got the unit mole inverse, second inverse. Okay, it is mole inverse into second inverse. Okay, so it is the rate of bimolecular quenching. Okay, now static quenching. What is static quenching? You see that in some cases, so now we are in a position to discuss what is static quenching. So, we discussed the simplest case of this collisional quenching, where we have this linear plot F0 by F versus Q. Okay. So, in some cases the fluorophore can form a stable complex with another molecule in the ground state. With another molecule in the ground state means, and that another molecule can be regarded as a quencher. So, if this ground state is non-fluorescent, this ground state complex is non-fluorescent, then you can call that the fluorophore has been quenched statically. Okay. In such cases, the dependence of fluorescence as a function of quencher concentration follows this type of relation, which is very similar to Stern-Volmer original relation, where in place of K there was KSV, where in this case Ka is the association constant of the complex, complex formation constant. In such cases the quenching occurs via complex formation, and this was first described by Weber. Now, the scheme is like this: M plus H nu giving rise to M star. So, normal, it is the normal fluorescence, so it will fluoresce normally. But in presence of quencher Q or the second molecule, this M forms a ground state complex, so that when you shine, it may go to the excited state, okay, or it may not also go. So, if it goes to the excited state, so what will happen, that it remains dark, no fluorescence is taking place because of this complex formation, and as a result of which what you get, that you get a similar type of F0 by F equal to 1 plus Ka into Q type of relation. Okay. So, the behavior wise, if you plot like F0 by F versus Q for the case where there is only static mechanism, then you can also expect a linear plot, normally a linear plot. So it is very difficult to diagnose whether the static quenching mechanism is operative or a dynamic quenching mechanism is operative, because both of them have the similar looking expression for the quenching plot, that is this F0 by F plot. Okay. So, association constant is the ground state association constant, is given by this Ka equal to Mq divided by M and Q, where Mq is the concentration of non-fluorescent or dark complex, M is the concentration of the uncomplexed fluorophore, Q is the concentration of quencher. Okay. So, so basically we have to look in terms of the association constant, and then from the association constant, from the expression of association constant, what we will do is we will just try to find out the concentration of the uncomplexed fluorophore, that can absorb radiation and give rise to fluorescence, that we would like to find out. So, that means M plus Q, MQ, it is a complex. So, Ka association constant is your, if it is a dilute solution, of course, otherwise you should have used activity. So, if it is a dilute solution, and of course, in fluorescence experiment, we always use very dilute solution, because of the fact that if it is concentrated solution or highly concentrated solution, then front surface absorption or inner filter effect may be operative, and therefore, signal distortion and some other complication due to inner filter effect or front surface absorption will come. So, you have to eliminate. So, the one way to eliminate is to dilute the solution, or maybe you should collect your luminescence very close to the place or the spot where the light first hits your solution, and in that case, and I mean this situation is rather tricky, but if you use in place of those concentrated solution conditions, in place of that if you use dilute solution, then Ka, I mean in that case your activity expression can be replaced with concentration. So, therefore, we I mean considering dilute solution and replacing activity by concentration, we are writing mq divided by m and q. So, this mq is the concentration of the dark complex, and these are the free quencher and m. Okay. So, free fluorophore and quencher, free fluorophore and quencher. Okay. So, therefore, we have to make use of this expression to find out this one. Okay. So, how to do that? So, the total concentration of the fluorophore, that is m0, that is 0 means when I mean at the starting point, that is equal to m plus mq. This is complex and this is uncomplexed. This is uncomplexed. Okay. So, Ka will be equal to so that means you just transpose it over here, m naught minus m divided by m and q. Okay. So, that means m naught divided by m, okay, minus 1 by, okay. So, now if we multiply both sides by q, then we get Ka into q, that is equal to m naught by m minus 1. Okay. So, what we get m naught by m is equal to 1 plus Ka into q. So, this is the expression what we get out of this this particular manipulation. So, let me write it again, m naught by m is equal to 1 plus K into q, and this m naught by m you can write as, because if m naught means when there is no quencher, m means in presence of quencher. So, if there is a 1-to-1 correspondence between, I mean there should be between the number of free m available for giving rise to fluorescence. Okay. I mean there is a 1-to-1 correspondence means the number of fluorescence intensity and this number of molecules which is available for giving fluorescence, this is basically 1-to-1 related. So, that what I mean to say that there is a proportional relation. So, using that proportionality relation, that when m is more you expect to have more fluorescence, if m is less you expect to have less fluorescence. Therefore, we can if we use this similar type of notation, then we can replace this with fluorescence intensity, that f naught by f is equal to 1 plus K into q. So, which is basically the the Stern-Volmer like expression. Okay, Stern-Volmer like expression, only thing is that it is relating Ka rather than Ksv. Okay. So, what we get out of this, if it is a purely static interaction, if it is a purely ground state complex formation interaction, then what is the advantage of such fluorescence studies? That if we can have two species which is thought to be interacting in the ground state, and of which one is fluorescent and the other one is non-fluorescent, or maybe other one will tend to form a ground state complex, giving rise to a dark complexation, then, or dark complex formation, then you know, from this fluorescence quenching study, that if we plot f naught by f as a function of this Quencher concentration, from this plot and the slope, I mean slope of the plot, we get the association constant. Okay, so the idea is that you have to have only, I mean 100% static interaction, 100% static interaction. Otherwise, if there is a mixture or something else is happening, then this situation will be further complicated. Okay, the situation will be further complicated. So that is why it is important to have you know, this static interaction, you know, primarily, then and only then you know, you can use this expression. Now the question, the standard question that comes to our mind, that then both of them are having, I mean both static and dynamic quenching, I mean plot wise, if we plot f0 by f, I mean if we have this quenching plot, I mean these two may look similar, I mean there is no basic difference, only thing is that technically one is Ksv, it is Ksv, and this is Ka, association constant. Now, how to diagnose it? The thing is that the option is that you can, if you, I mean one option is that if you have a temperature variation option, that if you can study temperature variation, I mean under different temperature condition, if you study this f0 by f, then we might have some idea. Okay. So, the idea is that if you increase temperature, then this collision frequency will be increased. Okay. So, collision frequency will be increased means you expect more quenching at the elevated temperature, but at the same time there is some complication that may happen, that if with increase of temperature, if its original, I mean original in absence of any quencher, original quenching, I mean original fluorescence is reducing due to some other non-radiative de-excitation, then it is a complication. That means if other non-radiative pathways are not that much affected, if only this collision is affected with increase of temperature, then and only then we can say that with increase of temperature you can have more quenching, if the mode is you know, if the mode is dynamic. So from temperature variation study we can diagnose in that way, but the point is, again there is a question that what is the guarantee that that the non-radiative modes are not affected. So how to know? So it's an involved question. Okay. And what will happen for the other thing, that is if it is a static mode with increase of temperature, if this binding interaction is you know, such that with increase of temperature, I mean if it is an exothermic process, I mean delta H is negative, then with increase of temperature you can expect to have weaker interaction, weaker binding. Okay, so first you have to know whether the process is exothermic, this binding interaction is exothermic or endothermic, and accordingly if it is, I mean if it is exothermic, then with increase of temperature you can expect to have weaker interaction, and therefore binding constant may be reduced. If binding constant is reduced means K is less, means your quenching will be less. So that means quenching F0 by F will be less with increase of temperature, but in other case if it is dynamic mode, you can expect increase of quenching. So this way you can grossly have some idea of whether it is truly a static interaction or truly a dynamic interaction. But the point is, there is another smarter way of knowing whether it is static interaction or dynamic interaction. I am just giving you the idea that since dynamic interaction, dynamic quenching occurs between the collision between the excited fluorophore and your quencher, that means excited state is really affected. Okay. So if excited state species, I mean excited state population is affected, and since lifetime is related to the excited state population and how quickly it is depleted, therefore you can say that excited state lifetime, I mean the lifetime of the fluorophore should be affected if it is a dynamic mode, but if it is a static mode, so your ground state is affected, there is no interaction in the excited state, therefore your lifetime should not be affected, or it is not at all affected for static case. So by measuring the lifetime in presence of quencher, we can get a definite idea or definite conclusion about the mode of interaction. Okay. So I guess today, I mean this much we should talk, and remaining things like complication of this quenching curve, I mean whether it is a upward bend or it is a downward bend, that will be taken up in the next class, and also a detailed account of this behavior of change of lifetime or no change of lifetime when, I mean in case of different modes of quenching, that will be taken up. So what we have learned today is various modes, I mean two principal modes of quenching. One is static mechanism, another is dynamic mechanism, and both of them are having the similar type of fluorescence quenching curve. Now you can diagnose whether it is static mechanism or a dynamic mechanism by change of temperature, but that is not a definitive, but you can get definite idea if we measure the lifetime of the fluorophore in presence and in absence of quenching. So that's all for today. So in the next class we will take up like complication of this quenching curve and associated issues. Thank you.